Today, we are going to begin a series of lectures regarding transient analysis of first order circuits. And I'm going to say that this is lecture one, and we are going to be talking specifically about what's called the natural response today. So there's a lot to unpack in this title. Okay. So let's kind of go through things bit by bit. So transient analysis is employed when a circuit undergoes a change. Okay. So, for example, we could have a circuit like this. So let's say that I have a current source connected to some sort of a switch. And let's put over here just some resistance R in parallel with some inductance L, like so. And let's say that the switch was closed over here at terminal B at t is equal to 0. The switch changes state and closes at terminal A. Okay. So our circuit would be undergoing some sort of change because the current source is being disconnected from influencing the behavior of the voltage drop and current through both the resistor and the inductor. Okay. So effectively, for any circuit that we're going to look at in this class, if it contains a switch and an energy storage element, so either a capacitor or an inductor, we are going to be dealing with a transient analysis problem. Okay. So first order circuits are simply circuits that contain a single equivalent energy storage element. So either some combination of inductances that can be reduced down to a single LEQ, or some combination of capacitances that can be reduced down to a single CEQ. If we can't reduce it down to a single energy storage element, then it isn't a first order circuit. So if it can be reduced down to 2 energy storage elements, it's second order circuit, 3 energy storage elements, it's third order circuit, and so on and so forth. Once you get beyond a second order circuit, the math just gets so ridiculous that we analyze them using what's called the Laplace transform. For those of you guys that have had Math 245, you're probably familiar with that. For those of you guys that haven't, have fun. You'll learn it sooner rather than later. Okay. So in circuits one, we're only concerned with the most simplistic case where we have a first order circuit. And so today we're going to look at both what I'm going to call RL circuits, so circuits that contain resistance and inductance, as well as RC circuits, which are just circuits that contain resistance and capacitance. Okay. So the natural response of a circuit or a system is what happens when any excitation sources are removed from the system, which is exactly what I have drawn here in this picture, right? The current source labeled as IS is being disconnected from the RL network and is just being applied across that short. So the RL network is going to have some sort of natural response that is due only to the values of those circuit elements and any initial stored energy, and it is not influenced by any external excitation because the source is no longer there to excite the circuit. Okay. So let's talk our way through some things here. Okay. So if we were to look at this circuit, so at t is less than or equal to 0 minus. So that means the time before the switch changes state, our circuit would look like something. And we'll talk about that. Okay. So we're going to make an assumption here. And the assumption that we are going to make is that our switch has been closed at position B for a very long time. So for such a long time that any transient condition or any change or response to change has already died out. So effectively for t less than or equal to 0 minus, we are looking at a DC circuit because the change has not yet happened. Okay. So for our simple DC circuit representation, here's terminal A. It's going to be open circuited. Here's our current source. It's going to be closed at B over here. Here's our resistance R. And here is our inductance L, like so. And so what I want us to think about here is what the inductor current is doing. So I'm going to label this inductor current as IL at 0 minus, because whatever it's doing the moment before the switch changes state is representative of what it's doing the entire time before the switch changes state, because it's a DC circuit. So there is no change. So I can encapsulate all of that information by evaluating the circuit at this particular single point in time. So since we're dealing with a DC circuit, I could replace my inductor with what? A short circuit, because we know from our class meeting last Friday that inductors behave like short circuits in a DC circuit. So I'm simply going to replace that inductor L with a short. So with that piece of information, what will IL at 0 minus be equal to? Say IS, right? So all of the current being supplied by our source will bypass that resistor and flow through the inductance because it's behaving like a short circuit. Okay. So what's the energy stored by the inductor at 0 minus? So what's the equation for energy stored by an inductor? It should be in your notes. 1/2 L times the current squared. So 1/2 whatever L is, times our source current squared. So as long as our source current isn't zero, then in this particular system, our inductor should have some amount of energy stored, right? So what I'm going to do over here is I'm going to make a graph. And we're going to kind of plot as we figure things out what's going on with the inductor current as a function of time. So here's IL of t. Here is t. And we just figured out that for all points in time up to t is equal to 0, our inductor current is some constant value, Is. Okay. So notice that for everything to the left of t is equal to 0, our circuit is at DC steady state, okay? Meaning that we're treating the circuit as if it were simply a DC system. That D looks like a P, so let me rewrite that. There we go. Still looks like a P, but whatever. Tired of writing that bit down. Okay, so let's look at something else, okay? So at t is equal to infinity. Now this may seem odd, so let me tell you what I mean by this. So this is just a long time after the switch has changed states and any transient response, so what's happening during the change, has died out. So if our transient response is over, it's already died out, then this also represents a DC steady state condition because our circuit is no longer undergoing a change, okay? So in this particular case, our circuit would look like this, okay? So now my switch is closed at position A. Terminal B is open circuited. Here's my resistor R. Here's my inductance L. Here's my inductor current, IL at infinity. And we need to figure out what IL at infinity is going to be. Okay. So once again, because we're at DC steady state, I could replace this inductor with a short circuit. Okay. And I want you guys to perform circuit analysis and tell me what IL at infinity should be. Say it louder, Ashton. 0. So our current at this particular point in time is 0. So there's a couple of simple reasons why we can infer that it is 0. The inductor is no longer connected to any sort of excitation source, and our transient condition has died out. So there can't be any current flowing through it. So what happened? Or actually, let's take this one step further. What's the energy stored at t is equal to infinity? Also zero. So I'm just going to call this 0 joules. Okay. So if this point here, just an arbitrary point, represents infinity, and I'll put it in quotes, some long time after our transient condition has died out, now our current is 0 again, and everything to the right of this line also represents DC steady state. Okay. So everything in the middle between 0 and infinity is what we're going to call our transient condition. And so this is how our circuit is responding to the change in our system. Okay. And we're going to need to figure out a mathematical model to describe what's going on. But before we do that, let's describe what's physically happening in the system. Okay. So for 0 plus is less than or equal to t is less than infinity. So this is what's describing the transient condition. Our circuit looks like this. Looks like this. So our switch would be closed at position A. Here we have our resistance R. Here we have our inductance L, and we're trying to figure out what IL as a function of time is going to look like. And we're looking for our inductor current as a function of time because we have a pretty large interval of time that we're interested in, right? So we're not going to get some single value here. We're going to get a function that's describing how our current changes from IS to 0 as the transient condition elapses. Okay. So at t was equal to 0 minus, we had some amount of energy stored in our inductor. Okay. At t was equal to infinity, our inductor no longer had any stored energy. So what happened to all of the energy that was stored by the inductor? The resistor gradually over time will convert that stored energy into heat because that's all a resistor can ever do. We talked about that on the third day of class, okay? So what we should expect to see is that since we know our inductor current cannot change abruptly, at t is equal to 0 plus, our inductor current has a value exactly equal to IS, and then our inductor current through some sort of path will decay to 0 at t is equal to infinity. And so what we're going to do here is we're going to figure out what that decay looks like. Okay. So in order to facilitate that, I am going to apply Kirchhoff's voltage law around this loop. Okay. So what I'm going to do is I'm going to define the voltage drop across my inductor like so. So we've got VL of t, and I'm putting the positive polarity terminal on top so that my inductor current flows into the positive polarity terminal. And now I'm going to define my resistor voltage as VR of t, like so. And the reason I chose to put the positive polarity terminal on bottom is because my inductor current is just going to flow around this closed path of just the resistor and the inductor connected to each other. So as IL flows up through the resistor, it'll flow into the positive polarity terminal if I define my voltage in that way. So applying Kirchhoff's voltage law, around our right-hand loop, we would simply have VR of t plus VL of t is equal to 0. Everybody okay with that? So we now have enough knowledge that we can express VR of t in terms of our inductor current, and we can express VL of t in terms of our inductor current. So for the resistor, we just use Ohm's law, right? So that's just going to look like R times IL of t. And for our inductor, we are going to have L times the derivative of our inductor current with respect to time. And so what we've accidentally just stumbled into here is a first order differential equation. Now I understand wholeheartedly that not all of you guys have had Math 245 yet, and so you don't have probably any experience whatsoever solving differential equations. So we, instead of applying math and calculus techniques, are just going to logically think our way through what needs to happen, okay? So we're going to make a guess for what form IL of t needs to have to satisfy this particular differential equation, okay? So what I have here is some constant value r times a function plus some constant value L times the derivative of a function have to add together to equal 0. So effectively what I'm looking for is a function that the function and the first derivative are effectively the same thing. So what mathematical function do you guys know of that satisfies that? An exponential function. So we're going to make a guess that our inductor current will be of the form A, where this is just an arbitrary constant that's just telling us how large our initial value of our exponential function will be, e to the st, okay? Where this s is what's known as the natural frequency of the system. And for those of you that have had Math 245, you may have also heard it called an eigenvalue for the system as well. Okay. So if I substitute in that particular guess value, I would have R times AE to the ST plus L times the derivative with respect to time of AE to the ST, and these have to be equal to 0. And so now I'm just going to perform that indicated derivative. So how do I take the derivative of AE to the ST? It's just bring the S down, right? So that's going to leave me with R times AE to the ST plus SL times AE to the ST is equal to 0. And all I'm going to do now is just rearrange that slightly so that we can sort a couple of things out, okay? So I'm going to put the A over here on the left-hand side. I'm going to have a factor of R plus SL, and then I'm going to put E to the ST over here on the right-hand side and set this equal to 0. Okay. So is everybody okay with the algebra that I just did there? Just move stuff around to put it in a form that I like. So let's talk our way through things here. Okay. So one obvious solution to this would be if A is equal to 0, then this is always true. While that is a solution, it is a trivial solution, and it effectively represents the situation to where our system didn't have any energy stored in it to begin with, so it's 0 for all points of time, okay? That isn't true for our system because we saw that there was energy stored in our inductor at t is equal to 0. So that's not the solution that we're looking for, okay? E to the st will trend towards 0 if s is negative, okay? But we can't necessarily guarantee that, okay? So if s is negative, and depending on what value s has, if we wait long enough, this thing might look like 0. But that's not really the way to go either. So we're going to have to look at this middle term, which is known as the characteristic equation. Okay. Characteristic equation for our system. And we need to figure out what value of s makes that middle term 0, because that will be a constant and it depends on the parameters of our system, namely our component values, okay? So R plus SL is equal to 0. What value of S makes that happen? Negative R over L. Absolutely right. So that is the natural frequency of our system, okay? And it unsurprisingly depends on the values of the components that we use in our system, because it wouldn't make any damn sense whatsoever for our response to not depend on what components we're using, okay? So from this, we now know that IL of t is of the form AE to the negative R over L times time, okay? So now we need to figure out what that A thing is, okay? So what do we know about an inductor? Well, we know that the current flowing through the inductor cannot change abruptly. So IL at 0 minus must be exactly equal to IL at 0 plus. So if we were to plug in t is equal to 0 into AE to the negative R over L at 0, we find out that A is simply equal to whatever value our inductor current had at t is equal to 0. So this is our initial condition on the system. Okay. So putting all of this together, we can say that for any first order RL circuit, IL as a function of time will have this form. So it will be IL at 0 minus for t less than or equal to 0 minus, and it will be IL of 0 plus multiplied by e to the negative R over L times time for t greater than or equal to 0 plus. So because we have this exponential decay that's going to trend towards 0 as time progresses, I don't need to add a third part of this piecewise definition for what's going on at t is equal to infinity, because this already takes care of that. Okay. So this is our equation for how inductor currents behave. So before we move on from this point and put this into practice, I want to make a couple of quick observations here. Okay. So we have shown that our inductor current during the time interval from 0 to infinity is going to be an exponentially decaying current. So on my graph way back up here, I'm just going to add that in. We would have an exponential decay like this. Okay. Where this would be is e to the negative r over L times time. Okay. So let's think about some things here really quickly, okay? When I'm looking at this circuit, now that I know what my inductor current is doing, I actually know what everything else is doing as well. So let me explain what I mean by that, okay? So according to Ohm's law, the voltage drop across my resistor is nothing more than the resistor value times my inductor current, right? So we could say for our particular system where we were just deriving things, I'm going to do this in blue because this is kind of a side-ish thing, but VR of t is nothing more than R times IL of t. So that would be whatever VR is at 0 minus for t less than or equal to 0 minus. And it would be whatever the voltage drop across my resistor is at 0 plus e to the minus r over L times time for t is greater than or equal to 0 plus, where this guy right here is nothing more than r times IL at 0 plus. Okay. Well, now that I know what my resistor voltage is doing, I can easily infer what my inductor voltage is doing, right? Because my inductor voltage is the exact same thing as my resistor voltage, except they're of opposite polarities, because those two elements are connected in parallel, but the resistor voltage has positive polarity terminal on bottom, and the inductor voltage has positive polarity terminal on top. So I could also just logic my way through finding that VL of t is just negative VR of t. So that would be whatever VL is at 0 minus for t greater, excuse me, less than or equal to 0 minus, and then whatever VL is at 0 plus e to the minus r over L t for t greater than or equal to 0 plus, where in this case, that's just negative R times IL at 0 plus. My resistor current is just the exact same thing as my inductor current. So effectively, what I'm trying to drive home here is that if one of our signals, in this case, our inductor current, is an exponentially decaying signal, then all of our signals have to be exponentially decaying signals. If they weren't, Kirchhoff's voltage law and Kirchhoff's current law would not be satisfied. Okay. So we can take our equation that we derived for an inductor and actually convert it into a generic equation that is valid for literally any circuit element in our first order system. Okay. So I'm going to say that y sub n of t, where that sub n is indicating the natural response, y is just a generic variable that could represent any current or voltage in our circuit, and it will be of the form y at 0 minus for t less than or equal to 0 minus, and it'll be y at 0 plus e to the negative r over L times time for t greater than or equal to 0 plus, and we can apply this single equation to determine literally any voltage or current in our system. So now that we know how things are going to respond, let's talk about this in the context of a circuit analysis problem. Okay. So I've brought a textbook here just so I can pull out some random example problem that's different than the ones that I've worked in previous years, just for shits and giggles. Okay. So let's say that I'm asked to analyze the following circuit. So here I've got some 12-volt source. Here is a 15 ohm resistor. And then here's a switch. And this switch is opening at t is equal to 0. And now I'm going to have a network containing a half a Henry inductance connected in series with a 2 Henry inductance. And those that equivalent inductance is in parallel with a 5 ohm resistance. And what I'm interested in finding is the current flowing through my inductors. And let's just say that I want the voltage drop across just this second inductance. I'm thinking about that voltage drop there. That's not in the textbook. I'm just thinking about how we could do that. And I'm thinking of a couple of different ways. So just as a warning, I might wind up scrapping that second bit here in a moment. So I'm going to put, maybe we'll do that. I think I can do it. So we'll see. Okay. So in order to apply the equation that we developed, we need to just effectively find the bits and pieces to plug in, okay? And so we're going to develop an algorithm to do just that. So our first step is going to be analyze our circuit at t is equal to 0 minus. So the moment before our switch changed state. So at this particular point in time, our circuit would look like this. So we'd have a 12-volt source in series with a 15 ohm resistor. At T is equal to 0 minus, our switch is closed. So I'm going to close my switch. Both of our inductors are going to be replaced by short circuits. Okay. So we're replacing them by short circuits because we're at DC steady state. So here is our current IL at 0 minus. And then over here on the outside is our 5 ohm resistor. So just for shits and gigs, let's put VL2 of 0 minus here. Let's see if I can make this work. I'm putting it as the voltage drop across both of those inductors in series, simply because they're legitimately both short circuits, so it's going to be 0 either way. Okay, so I'll have to figure out the rest in a minute. Okay, so how could I analyze this circuit to determine IL at 0 minus? Do I though? Because it looks to me like that 5 ohm resistor is shorted out. So I only have, yeah. So I think it's just going to be 12 volts over 15 ohms is 0.8 amps. 4 over 5 is 0.8, right? Yeah. By inspection, VL2, and I hope this doesn't come to bite me in the ass, but it's okay if it does, will simply be 0 volts because the voltage drop across a short circuit is always 0. Okay. All right. So there's our first step. Anything particularly wild or crazy about the analysis that we did there? So for our second step, we are going to analyze the circuit at a very specific instant in time. T is equal to 0 plus. Okay. So T is equal to 0 plus represents the exact moment after our switch has changed states. Okay. So we know then that our inductor current at T is equal to 0 plus has to be the same thing as our inductor current at T is equal to 0 minus, which would be 0.8 amps. It cannot be anything different or we would be violating the laws of physics. Okay. So at this particular point in time, this is what our circuit would look like. So we've got our 12-volt source. Here's our 15 ohm resistor. And now our switch looks like an open circuit. We've got our 2 inductors, so we'll come around to that in a moment. And then over here on the right-hand side, we've got our 5 ohm resistor. So now I'm going to talk about what I'm going to do with these inductors. Okay. And this is where it's making me a little nervous about finding just that particular inductor voltage. Okay. So we know that at exactly t is equal to 0 plus, and that's the only point in time we're currently interested in, our inductor current has a value of 0.8 amps. And the voltage drop across the inductor can be literally whatever it needs to be. Okay. So I'm going to choose to represent my inductors in this case by a current source. Okay. And the reason I'm choosing that is because at this specific point in time, the amount of current that is flowing through my inductor is a fixed quantity, while the voltage drop across my inductor can be whatever it needs to be in order to make the circuit work, which actually describes the exact behavior of an ideal current source. So I'm going to put a current source flowing down for both of my inductors. Okay. So the current source has to have the same direction as our inductor currents, and it also has to have the same magnitude. So these will both be 0.8 amp inductor currents. Now, as it turns out, we kind of glossed over this a little bit when we were talking about source combinations. Whenever I have two current sources that are connected in series and they carry the same value, I can replace it with a single equivalent current source that is just one of those guys. They're both forcing the exact same amount of current to flow through the same branch, so they are redundant. Okay. Now, what I lose in doing that is what VL2 is. Okay. So let me just be clear what I mean here. Okay. So if I have them both written like this, I would have here's my voltage VL2 at 0 plus. For what it's worth, I'm just going to put this in red up here, even though we're not particularly keeping track of it. So this would be VL1 at 0 plus. So when I combine those two current sources together, I'm throwing away the fact that there might be different voltage drops across both of those inductors. Okay. So in order for me to figure out what just that individual inductor voltage is, I'm going to need to kind of pull a little trick here. Okay. So this is my resistor voltage at 0 plus. And if we applied Kirchhoff's voltage law, what we would find is that my resistor voltage VR at 0 plus is equal to the inductor voltage VL1 at 0 plus the inductor voltage VL2 at 0 plus. That's just Kirchhoff's voltage law. Nothing particularly difficult there. Okay. So could we use circuit analysis to figure out what VR at 0 plus is? Let's start there. So how much current flows to the left? Anybody? Zero. Why? Because there's an open circuit in that path. Absolutely right. So zero current flows this way means all 0.8 amps has to flow that way, according to Kirchhoff's current law, right? So what's VR at 0 plus? So just Ohm's law. So we would have 5 ohms times 0.8 amps. And because the current is flowing into the negative polarity terminal, I throw a negative sign in front of my Ohm's law, and I get negative 4 volts. Okay, so now let's sort out what's going on with just the inductor voltage that we're interested in. I want to be clear here. I have dug myself into a hole, and so I'm just trying to get myself out of it. I wouldn't actually expect you guys to be able or have to do this, okay? But because I've set myself up this way and I'm an egotistical asshole, I'm going to get myself out of this pickle, okay? So even though it's never been taught in Circuits 1 before, I'm going to show you voltage division for inductors. So it's pretty easy, legitimately, okay? So what we have is a situation to where we have some known voltage, V of t, that is across 2 inductors connected in series. So this is my voltage V1, and this is my voltage V2 that I'm interested in, and here is my current I of t. So we know that V of t is V1 of t plus V2 of t, and this is going to be L1 di by dt plus L2 di by dt, or L1 plus L2 di by dt. So this would be way easier if we were dealing with impedances. I'm trying to remember how to make this math work correctly. Doing this in the time domain is hard. So what's going to wind up working out is that where V2 is just going to be V of t times a factor of L2 over L1 plus L2. So the voltage division for inductances works exactly like voltage division for resistances because they combine the same way effectively. So I'll do it in green here. This is, again, a quick aside that I wouldn't expect you guys to be to have to do. So VL2 of 0 plus would be negative 4 volts times 2 henries over 2.5 henries. So that's negative 4 times 4/5 is negative 16/5 of a volt, which would be 3.2 volts. Yeah, negative 3.2 volts. Yeah, sorry I dug myself in a hole and I can't super well explain how to do that or how to come up with that voltage division yet, but we'll get to a point where we could do it much more easily. That's literally our next topic. Okay, so hand waving aside, we were able, actually, we weren't able per se to do this. We didn't need to do any work whatsoever to determine our inductor current at 0 plus, because whatever it was at 0 minus, it has to be that. There is no other choice, okay? We then used that inductor current to figure out what was going on in the rest of the circuit at t is equal to 0 plus. So that's more of what I'm interested in for you guys, okay? So let's look at step 3. So for step number 3, what we are going to do is determine LEQ and REQ during the transient condition. So let me explain how we're going to do this, okay? So let's start by finding REQ. So I'm going to draw my circuit during the transient condition. So that means I've got my 12-volt source over here. I've got my 15 ohm resistor, an open circuit. Here I've got L1. Here I've got L2. Where this is the 1/2 Henry and this is the 2 Henry. And then over here on the right-hand side, I have my 5 ohm resistor, okay? So we're finding equivalent resistance. So that means we need to be looking at a dead network. So I'm going to turn off my 12-volt source. Okay. So essentially what we're doing is we're finding a Thevenin equivalent resistance. We're finding the Thevenin equivalent resistance with respect to our energy storage elements, okay? So that means I need to take my energy storage elements out and look in through the terminals that are left behind. What do I see? So just the 5 ohm resistance. A shorter way to do this would have been, hey, we know that the left-hand side of the circuit is disconnected, so there's only the 5 ohm resistor left, right? So it's the only thing that is impacting the behavior of the inductors. So REQ in this case is 5 ohms. Now that we know what our equivalent resistance is, we need to find LEQ. And that's going to be a similar process, okay? So effectively, we would be finding the LEQ with respect to that REQ that we just found. So here's our 15 ohm resistor. Here's 1/2 Henry. Here's 2 Henrys. I'm taking out my resistor and I'm trying to find LEQ. Well, very obviously, it's just those two in series. So LEQ should look like 2.5. I'm going to write that as 5 halves of a Henry. So just to recap here, because I see a couple of confused looks, and it's largely because I've got a circuit with multiple inductors in it. When we're finding the equivalent resistance, we're finding that with respect to our energy storage elements. When we're finding our equivalent inductance, we're finding that with respect to our equivalent resistance, because we're just trying to see what is influencing the behavior of the energy storage tank part of the circuit, okay? So the bit that we disconnected, we should never actually see that influence anything, okay? So I could have just as easily said that, hey, this part over here doesn't contribute anything. So LEQ is these two in series, and R must just be this guy. But this only works because this one is so trivial. So I'm trying to show you a more universal approach to get those results consistently, because this is actually one of the parts that I see the students struggle on the most, is finding the REQ, never the LEQ, because other than today in one in-class assignment problem, I will never give you two inductors in series or anything like that, okay? Or a combination of inductances or capacitances for these problems. Okay, so we found REQ, we found LEQ, we know what's going on at 0 minus, we know what's going on at 0 plus. So our last step is literally just plug stuff in to our equation. So plug info from steps 1 through 3 into our generic equation. So just to remind you all, our generic equation was our natural response, yn, is equal to y at 0 minus for t less than or equal to 0 minus, and then y at 0 plus e to the negative REQ over LEQ. Since we have equivalent resistance and equivalent inductance, that's what we're going to use, times time for t greater than or equal to 0 plus. So from that, IL of t is simply going to be 0.8 amps for all time less than or equal to 0 minus, and then it'll be 0.8 e to the negative, so let's see. So REQ over LEQ is 5 ohms over 5 halves of a Henry. So that should look like 2 per second. So e to the minus 2t. Amps for t greater than or equal to 0 plus. And then VL2 of t is going to be 0 volts for t less than or equal to 0 minus, and negative 16 fifths e to the minus 2t volts for t greater than or equal to 0 plus, where I literally just took the little bits and bobs from each one of our steps and plugged them into the generic equations. So just to be super duper clear here, this 2 simply represents REQ over LEQ. All right, so we've looked at a RL circuit. So now let's sort out how a first order RC circuit is going to work. And I'm going to do this derivation kind of quickly because it's practically the exact same thing. So let's say that we're interested in a circuit that looks something like this, or generically, right? So we've got some source voltage Vs. We have a switch that's opening at t is equal to 0. And now I have some resistance R and some capacitance C, like so. And I'm going to define this to be my capacitor voltage as a function of time, which is what I'm arguably interested in. Okay. So Following what we did with our inductor circuit, at t is equal to 0 minus, or less than equal to 0 minus, which is DC steady state, our circuit would look something like this, okay? So here's our source voltage Vs. Our switch would be closed. Here is our resistance R. Our capacitor C would look like what at DC steady state? An open circuit. So here is VC at 0 minus. So who among you guys can tell me what VC at 0 minus would be? Ashton, you looked down dejectedly, so I'm going to pick on you. What? So let me reframe the question. The capacitor and the resistor and the voltage source are all in parallel. What's the voltage drop across the capacitor? Vs. Yep. So what would the energy stored by the capacitor at 0 minus look like? One half CV squared, right? So 1/2 C times Vs squared. At t is equal to infinity, also DC steady state, our circuit would look like this. So we still have a voltage source over here on the left, but it is now disconnected from our circuit. Here's our resistor R. Our capacitor is once again going to be an open circuit because we're at DC steady state. So what should VC at infinity be? Zero. Because our source is disconnected, so our capacitor has been allowed enough time to discharge. That's what t equals to infinity literally represents, okay? So our energy stored at infinity must be 0 joules because there's no voltage drop across our capacitor. So we again have a situation to where our energy storage element had some amount of initial energy stored, and then it transfers it to the resistor, which converts that energy into heat as time progresses, causing the value of the voltage drop across the capacitor to gradually decay from Vs towards 0. Spoiler alert, it's also an exponential decay. We can prove that pretty easily, okay? So for 0 plus is less than or equal to t is less than infinity, although I guess it would, the less than or equal would be just as valid there. So this is during the transient condition. Our circuit would look like this. So here's Vs. Here's our open circuited switch. Here's our resistor R. Here is our capacitor C. This is the voltage drop across our capacitor as a function of time. And what I'm going to do is I'm going to define my resistor current as flowing down and my capacitor current as flowing down, so that both of those currents are flowing into the positive polarity terminal of the voltage drop that appears across those parallel connected elements. Applying Kirchhoff's current law, at the top right node gives me IR plus IC is equal to 0. I can express both of those currents in terms of that common voltage VC. So according to Ohm's law, that's going to be 1 over R times VC of t plus C times the derivative of VC of t is equal to 0. And I once again have a first order differential equation. So it stands to reason that I can use that exact same guess value to solve it. So we're now going to guess that VC of t will be of the form AE to the ST. Guessing that gives me 1 over R. Actually, let me just jump ahead really quickly. My stylus was being dumb. Give me just a moment. So subbing that in, we're going to wind up with A times 1 over R plus SC e to the ST is equal to 0, which means S would have to be negative 1 over RC in order to make that work. Okay. So from there, we have VC of t is equal to AE to the negative t divided by RC. And because we have a capacitor, we know that VC at 0 plus must be equal to VC at 0 minus. So that would be AE to the negative 0 over RC, which is just A. And putting those things together, we wind up getting our capacitor voltage VC of t will be VC at 0 minus for t less than 0 minus, or t less than equal to 0 minus, excuse me. VC at 0 plus e to the negative t over RC for t greater than or equal to 0 plus. And we can generic this guy up as well. Since the voltage drop across both of the elements are the same, we can use Ohm's law and all that kind of stuff to find the currents have to be that as well. So generically, our natural response for this RC circuit will be of the form Y at 0 minus for t less than or equal to 0 minus, and then Y at 0 plus e to the negative t over RC for t greater than or equal to 0 plus. So it's effectively the exact same expression, except that now we have a different scaling factor of time in our exponential decay. I know I went through that super quickly, but we spent a good amount of time putting it all together for the inductors, and for the capacitor, it's pretty much the exact same relationship. All right, so let me find a capacitor problem that we can work that isn't going to be too much of a pain in the butt. So as an example, let's say that we have the following circuit. So let's put a 15-volt source here. And a switch that is opening at t is equal to 0. Here's a 3 ohm resistor. Here is a 50 millifarad capacitor. Here's a 10 ohm resistor. And here is a 7 ohm resistor. And I am interested in us finding VC as a function of time, as well as this voltage VR as a function of time. So our steps are going to be practically identical to what we did in our inductor problem. The only change we're going to make is actually in step 3. So instead of finding LEQ and REQ, now we're going to find CEQ and REQ. Okay. So step 1 is still analyze the circuit at t is equal to 0 minus. So that would look like this. We would have our 15-volt source. Here's our 3 ohm resistor. What's our capacitor going to look like at t is equal to 0 minus? An open circuit. So here's VC at 0 minus, excuse me. Here's my 10 ohm resistor. Here's my 7 ohm resistor. Here is VR at 0 minus. So how could we find either of those things? What was that, Ashton? KVL. That can definitely be part of it. I feel like there's an easier way. Voltage division. Yep. So that's how I would do it, voltage division, because I'm trying to do things efficiently. So we could say that VR at 0 minus would be 15 volts times 7 ohms over 3 ohms plus 10 ohms plus 7 ohms. So 7 times 15 is 105 over 20 volts. I am aware that that can be simplified. I'm also aware that I'm lazy, so I'm just going to leave it like that. What about VC at 0 minus? We could do voltage division for that one as well. So the capacitor is effectively in parallel with the series combination of 10 ohms and 7 ohms. So I'm going to do 10 ohms plus 7 ohms in the numerator, and then 3 ohms plus 10 ohms plus 7 ohms down here. Let's see, 17 times 15 is going to be 225 plus 30, so 255 over 20. If I did that mental math correctly. Yep. So anybody have any questions, comments, or concerns about the analysis that we did here at 0 minus? We could have done KVL around the loop, finding the current, and then use Ohm's law to find the things, but I want to do it in one step when I can. So nothing wrong with your suggestion at all, but voltage division got us there a little bit quicker, so that's why I like it. All right, step number 2. So here we are going to analyze our circuit. At t is equal to 0 plus. Okay. So at t is equal to 0 plus, our 15-volt source is disconnected. So our switch is open. Here's our 3 ohm resistor. We'll talk about what the capacitor is doing in a second. Here's our 10 ohm resistor. Here's our 7 ohm resistor. And then our capacitor is here in the middle. Okay. So because we're looking at the circuit at exactly t is equal to 0 plus, the moment of time after our switch change states, we know that VC at 0 plus must be equal to VC at 0 minus. So this has to have a value of 255 over 20 volts. Okay. Literally cannot be anything else. The current flowing through the capacitor can be whatever it needs to be. Okay. So what are we going to represent the capacitor with here? So we represented the inductor as a current source at t is equal to 0 plus because the current was fixed and the voltage could do whatever we want. Now we have a situation where the voltage is fixed and the current can be whatever it wants. So I think this is going to look like a voltage source. So we just need to make sure that our voltage source has the same polarity as VC at 0 plus and also, or excuse me, 0 minus and also the same magnitude. So this is going to look like a 255 over 20 volt source. And then here is the VR of 0 plus that we're interested in. How are we going to find VR at 0 plus? Connor, tell me what to do. All right, so you guys are not seeing what I think is the obvious thing, so I'm going to be an asshole and point this out. I have a voltage source, and then I have two resistors connected in series. So I have a known voltage drop over resistors in series. What am I supposed to do here? Voltage division, yay. I pointed to you because you were the one that suggested it for the previous thing. Yeah. So we'd have 255 over 20 volts times 7 ohms over 10 ohms plus 7 ohms. 255 over 20 times 7 over 17 gives me 21 over 4, which is the same 105 over 20 that we had earlier. I thought that was going to be true, but I wanted to double check. Oh, and that should be volts, not ohms. So step number 3. Will be to determine CEQ and REQ during the transient condition. So during the transient, our switch is opened. Here's our 15 volt source. Here's our capacitor of 50 millifarads. Oh, there was a 3 ohm resistor right here. 10 ohm resistor. 7 ohm resistor. Since we're finding Thevenin equivalent resistance effectively, I'm going to turn that source off. And we're finding the Thevenin equivalent resistance with respect to our energy storage element. So I'm going to take the energy storage element out, replacing it with an open circuit. And what do we see looking in to the terminals left behind by our energy storage element? 10 ohms in series with 7 ohms. Why don't we see the 3 ohm? Because it's open on the other side. Yep. So REQ is just 17 ohms. But CEQ? Well, there was only one capacitor, so it kind of has to be that. So for what it's worth, REQ times CEQ is 17 times 50 times 10 to the negative 3, 0.85 seconds. So 1 over REQ over CEQ. Goodness, that first Q looks terrible. Second Q doesn't look much better. Is 20 over 17 per second. The reason why I'm writing it that way is because I know that I'm going to have T divided by REQ over CEQ. So it's going to look like 20 over 17 times T when I put it in my final equation. So I'm just getting ahead of myself there. All right, so step 4 is simply plug stuff in. To our generic equation. So VC of T, so what was the capacitor voltage at T is equal to 0 minus? 225 over 20, right? So 225 over 20 volts for T less than or equal to 0 minus. What was the capacitor voltage at 0 plus? Same thing because it's not allowed to change. Okay. So 225 over 20 e to the negative 20/17 t volts for t greater than or equal to 0 plus. Our resistor voltage was 105 over 20 at t is equal to 0 minus, and it was the same. So I wrote it as 21 over 4, but that's the same thing as 105 over 20. E to the negative 20 over 17 t volts for t greater than or equal to 0 plus. So this process that we've developed for both RL and RC circuits will work for literally any circuit that contains a single equivalent resistance and a single equivalent capacitance, or a single equivalent resistance and a single equivalent inductance, where we are disconnecting our excitation source. Doesn't matter if it's a current source or a voltage source from our system. Okay. So what you guys are going to be watching a video on Friday, because again, I'm not going to be here because I've got a board meeting, will be what's called the total response of RL and RC circuits. Effectively, what happens if we switch in our sources instead of switching them out? So we're just going to be mathematically describing effectively how a capacitor charges, because today we were talking about how a capacitor discharges, things like that. In the grand scheme of things, it is a very small change in our analysis procedure. Effectively, the only thing that's going to happen is that what's going on at t is equal to infinity will no longer be explicitly 0, and so we need to take that into account. Everything else is the same. All right, so that is enough ranting out of me for today. So you've got, oh goodness, only 20 minutes to work on the in-class assignment. Sorry for talking so damn much. If you have any questions, please let me know.